Okay, so um, okay. So basically in the last class we started with তোমরা দেখতে পাচ্ছ এবং শুনতে পাচ্ছ?
Yes, sir.
Okay, so in the last class we left with the some part of Bose ideal Bose system, Bose gas, and I will quickly go over the part which I went through in the last class, that we do not confirm the condition this, because this corresponds to when it is pretty small, this quantity n, little n lambda q, n is the density. Then when it is pretty small, then it goes over to the classical. It represents the classical picture, right? Classical case, because when n lambda q is tending to zero, means lambda tending to zero, it happens only when the temperature is pretty large. Okay, so it corresponds to a classical regime. Now, for small but not negligibly small, yet small value of n lambda q, the various quantities pertaining to the system can be expanded in the power series of this parameter. Okay, and also you will see a kind of departure from the classical values will set in. Okay, when n lambda q becomes of the order of unity, that then not only does the behavior of physical system exhibit a significant departure, as I said, from the typical classical behavior, but it also influences by the fact whether the system obeys Fermi-Dirac statistics or the Bose-Einstein statistics. Okay, it also depends on the statistics at that, when this parameter goes over to the unity. Okay? So these are the things, kind of informations. With these informations, now let us look at the statistical quantity that or thermodynamic and statistical connection, that PV by KT is ln. This is the grand partition function, and we have already explained that it in a combined manner it takes this form, where a0 corresponds to Maxwell-Boltzmann distribution, a equals to -1 corresponds to the Bose-Einstein distribution, and +1 corresponds to the Fermi-Dirac distribution, and corresponding the number of particles is given by this summing over the occupation number, average occupation number, or most probable occupation number. And then PBKT can be written in this form. This one you put a equals to -1, and then for both cases you can write this, and for n equals to you can write this. And this is the fugacity. We are already quite familiar with this term, fugacity, which is basically exponential mu by kt, and beta is 1 by kt as usual. It's the usual notations. Now, since we are dealing with a system which is very large in volume, and therefore the spectrum of the system will be very in a continuous nature, right? Because you cannot distinguish two energy levels close to each other, successive levels. Since volume large, spacing will be pretty small, and therefore the energy levels will appear to be very continuous. And we know these are non-interacting system we're talking about. The particles are non-interacting, and therefore free particles. So for free particle, you know the dispersion relation, how the number of states go with energy, and that is we have already derived this earlier, and this is the expression for the density of states. And therefore if we go over from sum to the summation to the integration, from the discrete to the continuous system, then we have to go over from summation to the integration using this density of states expression. Well, there is a kind of word of caution that you have to be aware of, that when you are summing over, or you are when you are representing the summation by integration, then if you take the density of states into account, then you see for zero energy, for energy zero, the weight factor is becoming zero, because this integration is entirely zero. So the zero expression, the expression for zero, where is it? Sorry. Is it? Where? Okay, so basically, if you as I said that I'm not going to entertain any more person if it appears in between. Anyway, so basically, if you go over from summation to the integration, basically you are avoiding, just if you take this integration, you are avoiding or you are neglecting or you are losing the contribution for epsilon equals to 0. That's why in the summation, that you have the expression summation sum over epsilon, then epsilon equals to 0 contribution is taken separately, and that's why you have this term which corresponds to epsilon equals to 0 term, and the rest say epsilon non-zero. And this, even though you have taken the limit epsilon equals to 0, but as for epsilon 0, this term does not contribute, and therefore taking that for convenience is okay. Now, similarly, n by v, you have the similar kind of expression, it follows. And note that epsilon 0 term in the integral is not giving to contribute. I had already explained that in this case, that epsilon 0 term is not going to contribute from this integration. We have already taken that into account here. Now, well, you see, as we discussed earlier, the distribution curves obeying BE and FD statistics merge the classical distribution when, and this, in this case, this parameter A is irrelevant, right? Because Maxwell-Boltzmann distribution is a classical distribution. It is 1 by e to the power epsilon minus mu by kt. Then A is not important. Okay, so A will not be important, it will not be important. And also that we go over to the classical regime only when t tends to infinity. As in, at large temperature we go over to the classical limit, and therefore, so if t is large, then it has to be irrelevant, then this term has to be much greater than 1. And then if t is large, then mu has to be negative, and the magnitude should be large. That is what it says. And therefore z, the fugacity, e to the power mu by kt. Mu, if mu is negative and large in magnitude, then it has to be less than 1. That means when z is pretty less than 1, then it corresponds to the classical. Well, but on the other hand, when z will approach 1, then it will show the quantum behavior. Okay, therefore, when z is pretty less than 1, corresponds to the situation not for remove from classical limit, and the term this and this, you can see they will be simply pretty small. So when z is small, pretty small, then these two terms, I mean that 0 epsilon 0 terms, that means this term and this term, they are negligibly small. So however, as you see, just note this: when z is pretty small, then you can avoid these two terms. Okay, in these expressions, you can avoid this term and this term. Okay, neglect it because pretty small. However, if z increases and assumes the value close to unity, then the term z by, this is the, I think, n0 by v, number of particles, n0 by v. Okay, this one you say n0 by v, n equals to this plus n0 by v as far as dimension is concerned. N0 corresponds to the number of particles in the ground state. Okay, so you see that as z increases, and the value approaches close to unity, the term z by z 1 minus z v, which is identically equal to n0 by v, which is of course a significant number, right? Significant fraction of the quantity n by v, and this accumulation of a macroscopic fraction of particles to a single state, basically ground state, leads to the famous phenomena of Bose-Einstein condensation. So this gives you an idea about the Bose-Einstein condensation from the expression that z tends to 1, then it is a substantial number, and those corresponds to the ground state particles. Okay, particles in the ground state. So there would be an accumulation of particles in the ground state, and that is what is called is basically a signature of Bose-Einstein condensation. Now see n0 by v. Now you see when z is about 1. Okay, then you know that n0 by v is no more a small number. It is a large fraction of the particles, and therefore from this expression you can see that that 1 minus z corresponds to 1 by n0 plus 1, and therefore this expression should be v inverse ln of this inverse. This is of the order of n inverse ln n. And you have seen earlier also, I also asked you to check in the computer that this of the order of this value is also very small for large n. Okay, and therefore you see for z less than very less than 1, both the terms, both the terms with pvkt and n by n0, n by v, both the terms are negligible. But when z approaches 1, then this term is negligible, but other term is not negligible. Okay, and therefore, so this term is not negligible, but or rather I would say in the expression, this term is negligible but this is not negligible. Okay, and therefore you can drop this term altogether and go ahead, okay, for further discussion. That is what we will be doing. That p by kt equals to this. We have left the other term, the additional term we have just forgotten, because that is negligible for z less than 1, very, very less than 1, and z approaching 1 also. So in the interregime of our interest, where z belong between 0 and 1, this value, the additional term is negligible, and therefore there is no point of carrying over that term along, and therefore we neglect it. And this is, of course, this is not small, and therefore n0 by v, that I mean the number of particles that is accommodated in the ground state is included here. So now at this moment you have these two equations, 3 and 4. Okay, and you have to go over. And in the meantime, let me tell you that if you see that you cannot hear me, or there is internet problem, then just give me a message in the WhatsApp group. Okay, so p by kt is this, and now you have the change of variables. You represent x as beta epsilon, and then do this. I think you have done it in the last class, and eventually you will have this integration that can be carried out by integration by parts. And the first term, the second term, first term will be 0 actually, and second term will be left with second term, and eventually it will turn out to be this. And then this gamma of 5 by 2 can be written in this form, and therefore this 3 by 2 is replaced in terms of gamma function, and eventually you have this formula, and therefore p by kt is, if these things are already there, you have seen, and along with that this term, and therefore if you simplify it, p by kt would be 1 by lambda cube this and this. Okay, now you see, so p by kt is, I have rewritten this form. Now let us encounter, or let us write a function gnz, which is, say, basically you were writing this as gnz, and which is basically x to the power n minus 1. It is 5 by 2. It is a general formula. N minus 1 by z inverse this, and 0 and 1 z is between 0 and 1. The limit z tending to 0, what is the value of this when z tends to 0? The limit z tends to 0, if you do this calculation, you will find some kind of simplification, and you'll find this is z x to the power minus 1 e to the minus x, and this kind of z gamma of n, right? Z gamma n. Now you see this function, it reduces to z gamma n. Gamma is a constant, right? Constant will be there, but this z, now the function, it should be a function in general, it should be a function of z, which for z tending to 0 becomes z, right? And therefore you can write is gamma n, that factor will be there, and along with that there is a function, you can write it as g and z, and this g and z will become z when z tends to 0, right? And therefore g and z, and this capital Gn can be written as gamma n g and z, and therefore g and z equals to 1 by gamma n this, and therefore you see it is very similar to this, right? This one. So you can write this as g of 1 by lambda q, g of 5 by 2 z. Okay, that is what we have written here. Where is that? We have not written here, but we can write it certainly like that, because g and z is this, and therefore you can write it as g5 by 2 z. Okay, this one. Okay, now you see for small z, again, if it is z is small, then you can rewrite it in this form, and then you can write this as where z is very small, and therefore you can have write it in a summation, in a series, expand it in series, and therefore eventually we'll have these will follow. So if you just go over line by line, it is nothing much complicated. It's pretty simple, and this you can write as z to the power l, and take all these together. Different, this is integration over x. You just rewrite the variables in terms of xl, and that is what is named as xi, and z to the power l by l to the power n. If you take these together, l to the power n, 0 to infinity. Okay, so just look at it once. Okay, what you have done, you have taken it to the numerator like this, and you have expanded this, and then you have written the next step: x to the power n minus 1, then z x to the power, then you have coupled these two terms together, this to the power l minus 1. Where is that? It's z x to the power minus x whole to the power l. Where is this? Oh, okay. So then you have to make l equals to 1 to infinity, right? If you make it l, because it will be l equals to 0 to infinity, then you have to the power l plus 1, right? And that you have written l equals to 1 to infinity, and you have made it l minus 1 equals to l. Okay, and then dx. This is the term you have written, and then z to the power is taken out, then x to the power minus 1, e to the power minus xl, and dx. And you write everything in terms of xl, because in the exponential you have xl, and therefore z to the power l, then x l to the power n minus 1 by l to the power n minus 1 is the minus xl, d of xl by l, and l n minus 1 and l, they combine together gives you l to the power n, and then integration. If you write xi equals to xl, then it is xi to the power n minus 1. এখানে তুমি কেন লিখতে পারো সে xi equals to say x, that you can write this I to n minus 1 and this z to infinity, and of course this is a gamma function and this is gamma n. So you can write it as gamma n cancels, and it is summation l equals to 1 to infinity z l by l. Now thus for z pretty less than 1, as I said that g and z is z. I already told you earlier, right? G and z is z. Now come back to the expression p equals to and remember that you can write in this in terms of this series only when the series converges. Okay, that you have to be careful. Now see, come back to the main expression that p by kt is the g5 by 2j. I already talked about it, right? It is written here. P by kt is 1 by lambda q g5 by 2j, and g5 by 2j already we have explained what is the form, right? Like this. Well, now you see. N minus n0 by v, again we have this expression. So now at this moment, after doing all sorts of things, basically we have 5 and 6. These two expressions are the main expressions here. Okay, we have to now carry over, or we have to go ahead with these expressions, these final expressions. Now you see, if you eliminate z from this, because you see the parameters, the p, k, t, lambda, and all these things, n. So if you if you have the elimination of z from these two, then you will have a relation between p, k, t, n, v, and so on, and therefore that will give you the equation of state for the Bose gas. That is equation of state for the particles having the, the non-interacting particles, which is obeying the Bose statistics. Well, having said that, the internal energy of the system is given by this. Okay, let us check whether it does produce the, some known results or not. U is, del del beta, this Z and V constant, and this is the partition function. And PV by KT is ln of Q, P by KT, then you can, you can just P by KT expression, you already have this one, right? So you just substitute this and del del T, you will see that this turns out to be like this, and eventually will have like this. And you see that what do you obtain? You see that P by KT, what is the expression for P by KT? P by KT is this, 1 by lambda Q G5 by 2 this, right? And you obtain, this reproduces some kind of stuff here, right? This is what is 1 by lambda Q. This is nothing but P by KT, right? So then 3 by 2 KTV, and this part 1 by lambda Q G5 by 2 G. Z, I said this is G and this is Z, okay? Now like Z, okay? Then you see this is P by KT, you put it here, and then if U equals to 3 by 2 KTV, P by KT, KT and KT cancels, and therefore P equals to 2/3 U by V. This is the energy density. So pressure is basically of the order of, it's a 2/3 of energy density, right? This is kind of relation we already know. Okay, this is reproduced. Now, if Z is small, we can make use of the expansion, right? This, if Z is small, then we can use this expansion, then it will converge. Okay, that is what I said, that you must care about the convergence of the series. Okay, so G and Z is this, and at the same time, n naught, n naught expression, that is Z by 1 minus Z, because n naught by V, you got 1 by V Z by 1 minus Z, right? And therefore, when Z is small, definitely it's pretty small, because and compare, it's almost pretty small. Of course, I mean, compared to the total number of particles n, and hence the expression n minus n naught by V equals to 1 by lambda cube g of 3 by 2 z. And if z is small, then of course it will give you the first expression, only z, right? It will be, then you can neglect all others because they will not, they will be pretty small, right? And therefore, n by v is this, g and z equals to z, and therefore n by v equals to this, equals to z by lambda cube, because this will give you z, and therefore z equals to n lambda cube. And n is this. Then pt, p by kt is 1 by lambda cube, g 5 by 2 z, and PV by nkt equals to 1 by n lambda cube, right? V by basically you divide by little n here, right? And this n by v, so v goes into the numerator, PV by nkt 1 by n lambda cube. Then this is function of z n lambda cube. So you can see that in terms of series, and this series n lambda cube L equals to 1 to this, no, Z is n lambda cube, basically. You see, Z is n lambda cube, and therefore you can write this series. Earlier, I mentioned, if you remember, that n lambda cube may be a parameter in terms of which you can expand the physical quantities or expressions of your interest. Now, n lambda cube to the power L by 5 by 2. Therefore, you can write in terms of a series of n lambda cube, and it turns out to be like this, where the coefficients, okay, you just remember these coefficients, okay, or you can no or you can have from here also, but these are the coefficients we'll have if it is expanded in this form. Now look at these coefficients. When you're at high temperature, means n lambda cube tends to 0, right? When it tends to 0, then you return the first term only, right? Then L equals to 1, that means you have only A1. Okay, A1 plus something this to the power 1 and so on. But since it tends to 0, then I return only the first term. And therefore A1 equals to 1 here, and therefore PV by NKT equals to 1, and therefore it reproduces the classical result. Okay. So at high temperature, again I repeat, tends to 0, and therefore if you expand it, where you can expand, and these are the coefficients you see, you just return the first term because this tends to 0. These will not contribute anything roughly, and therefore the equation of state turns out to be PV by NKT equals to 1, P equals to NKT. However, if note that for small n lambda q not tending to 0, that is, it's a kind of moderate temperature, so that n lambda q is not that small. It means that you don't just terminate the series in the first term, you just consider the second term or third term, because they will also contribute a little bit, but those coefficients are negative, you see, and therefore your PV is less than NKT, or PV by KT is less than 1, right? It will be 1 minus some value and so on, and therefore it means that the pressure reduces. Okay, P will reduce. The system volume you have the same volume, so the condensed particle do not contribute to pressure. The signature of condensation to the ground state with epsilon 0 is this is the kind of signature, right? When you see that when you have that n lambda q, which is z, which is not tending to 0, but it is some kind of moderate value. Of course, it is between 0 and 1, and when it is having a moderate value, then the pressure is becoming less than the normal pressure. Okay, so classical gas pressure, whatever the pressure is for the classical gas, but if it is a Bose gas, and it is this parameter is going to be, it is going to depart from the classical one, then that statistics tells that this will have a less pressure. Okay, so these are the manifestations of the statistics only. Okay, quantum statistics. Okay, the pressure will be less. PV by NKT is less than 1, and implies the pressure is less. Pressure less, why? Because many of the particles will condense to the ground state, which will not contribute to the pressure. Pressure will be coming from the excited state.
স্যার
Yes.
বলছি একটু মানে আগের পেজটাতে যান।
Hmm.
হ্যাঁ মানে এখানে নেগেটিভ গুলো কেন হলো, কোফিশিয়েন্ট গুলো আরেকবার বলেন তো, মানে A2 A3 আর A4টা।
না না এইগুলো কেন হলো, মানে these are the expressions. I have picked up the expressions. Okay, these are the results. Okay. So I have not seen how these coefficients came out. For example, if you do the Fourier series, okay, then there is a way of finding the coefficients. Okay, there is of course a way if there is a series finding the coefficients. I have just picked up the values. Okay, and I am explaining physically what are the how it is affecting the parameters, physical quantities, macroscopic quantities. Okay.
ওকে স্যার।
So I'm not going to dig out how you obtain the coefficients. All I'm saying that these are the first four coefficients you have if you expand it. Okay, if you expand this g function, okay, then you will have if you expand it in terms of this n lambda q, which is z, then you get the values which will the coefficients will be like this. Now I explained that when it is tending to 0, then you just return the first term because other terms are not going to contribute, and therefore PV equals to NKT, and that is what is the classical value because you are in the classical regime. But if you depart from the classical regime, as we have explained earlier, then you see that these negative coefficients are going to appear because you don't terminate at the first value, right? First term. Then you go over to the second term, third term, because this value is not actually tending to 0. It can have some finite value, but of course less than 1, otherwise it will not converge. Okay, and then your pressure is going to be reduced. That is what I said. And physical explanation is, of course, that means that in this region, as z tending to increase, then some of the particles, you have seen number of particles at ground state, that z by 1 minus z or something like that. If z is going to increase, then it is going to be a substantial amount, and therefore number of particles, some fraction of number of particles are going to occupy the ground state, and ground state will not contribute to any pressure. Okay, and therefore the pressure will come from the excited states. That means the condensation has started. That is what I wanted to convey. Okay, Mosumi.
ওকে স্যার।
Now, if you look at the specific heat, then again you can calculate. You just do the calculations at home. That's Cv by nk equals from nk del u del t and pvkt. If you just put these values, and eventually you will find that this kind of stuff you will obtain. Okay, and again, if you have calculate the coefficients, then the coefficients are, I'm not going to calculate the coefficients, but a few coefficients I'm going to take, which are the first few coefficients. Okay, so this is 1, first coefficient is 1, second is this, third is this, and so on. Okay? So this is the coefficient. Now if you see, so this is the specific heat of the system, okay, of the gas. Of course it is a non-interacting gas. Now you see, as t tends to infinity, lambda tends to 0, and therefore n lambda q tends to 0. Okay, that tends to classical gas. Then Cv, then if it is tending to 0, then you terminate here because you don't take into account of this, because they will give nearly zero contribution, right? And therefore you see Cv equals to 3 by 2 nk, and this is what is the classical value. So the classical result is reproduced here, right? Now, if you think that no, it's not, temperature is not infinite, it's kind of moderate, and then in lambda q is not actually tending to zero, but small, but not tending to zero. In that case, you have to consider a few more terms, right? Then you see this is one, and then these are going to add something. These coefficients are positive, right? And therefore they are going to add something. And therefore you see the specificate, if you have a classical value at some but temperature, it is going to increase because these terms are going to add up to the n 3 by 2. It is going to add up something, right? And therefore it is going to increase. However, when temperature is tending to zero, then the specific heat has to go to zero, right? So then you see, now if you think the asymptotic cases, like, so initially it was increasing. No, at T infinity, it was reflecting the classical value 3 by 2 n k, and then as T is decreasing, no, it's a kind of moderate value. It's decreasing, and when it reaches a moderate value, then the specific heat is increasing, and then it is when it is going to zero temperature, then specific heat has to go to zero, and therefore it tells you that there is some kind of maximum. Okay, and consequently it must pass through a maximum, and we will show that the maximum is a natural cusp, and it appears at a some characteristic temperature which is called Tc, and the deviation, the derivative of the specific heat will be found to be discontinuous at that temperature. So it can be shown that and the specific heat actually, it will 3 by nk2. If you plot with 1 by t, then t infinity minus 0, that means there it will have a 3 by 2 nkt, and then eventually it will go to a maximum value, and then it will decrease. Okay, there will be a cusp. Okay, and at the cusp, at the point, so there is a particular temperature at which the peak of the cusp, and or that cusp appears, and there the derivative will be discontinuous. If the derivative is just discontinuous, in the specific heat, if it is discontinuous, then the transition, some kind of phase transition, it indicates that there is some kind of phase transition. And since the specific heat is the first derivative of the energy, and therefore the discontinuity will appear in the second derivative of energy, because the CV itself will have a discontinuity at TC. Then that is called second order phase transition. Okay, if the first order of energy, the first derivative of energy, if that becomes discontinuous, then it is called first order phase transition. And if the second order derivative of the energy becomes discontinuous, it is called the second order phase transition. This is just for your information. Okay, so basically from this expression, that you can have an idea that at t tending to infinity, it is 3 by 2 nkt. But if it is not that high, moderate temperature, then this term will add up, and therefore it will give you larger than this. The specific heat will be larger than this. But if you decrease the temperature to zero, then certainly it will give you zero, and therefore there is a maximum, and that maximum is basically kind of a nature of the maximum is kind of a cusp, and at the cusp, that derivative becomes discontinuous, and that would be the second derivative, because derivative in CV is discontinuous. That means the second derivative of energy is discontinuous, and therefore that would be called uh, it represent kind of second order phase transition. But anyway, now uh, that we have already said, but again, let's see, as temperature of the system falls, and hence the value of the parameter lambda q by p grows, the expansion of this type, this is no more useful. That is also true. Therefore, we have to work with this, because otherwise, because it will not be kind of converging stuff. Okay. So now let us again recall these original equations that P by Kt is this, U is this, and precise value of Z is obtained from the relation this, right? N by N minus N naught by V equals to this, where N0 is Z by 1 minus Z that we have seen, and therefore N minus N0. Now look at this carefully. Now N minus N0 is Ne. We denote is Ne. Ne means number of particles in the excited state. Okay, N0 is the number of particles in the ground state. Now, because n0 is z by 1 minus z is small value, small unless z is approaching unity, right? Then z is obtained from this equation. This n minus n naught is ne. So ne by v, ne by v is 1 by lambda q g3 by 2 z. Okay, this is the equation. It is obvious that for 0 less than equals to z less than equals to 1, the function this g3 by 2 z is increasing, okay, monotonically with z, and is bounded its largest value being g3 by 2 1, because z is limited between 0 and 1. Then g3 by 2 z that will be bounded by g3 by 2 1, okay, and that value is we denote as xi of 3 by 2, and this is you correct it properly, write as xi or something like that. 3 by 2 is a 2.612. This value is this, okay. Now you see, so maximum value of this, okay, is this, okay. So it cannot go beyond that. Now come to this expression. Hence, for all z of interest, g3 by 2 z is less than this, because this is the maximum value when z equals to 1. Okay. Now, consequently, for given values of v and t, the total number of particles in all excited states taken together is also bounded. That is, Ne should be, because any expression is, where is the any expression? This, right? This. And therefore, and lambda, the thermal wavelength. And therefore, you see that Ne by V has to be less than equals to 1 by lambda q I 3 by 2. Because G3 by 2, Z maximum value 1, so maximum value is this, and therefore Ne. So number of particles accommodated in the excited states is should be should be less than equals to this number. Okay, so as long as the actual number of particles in the system is less than this, then everything is okay. Okay means, but practically all the particles are distributed over all the excited states, and the precise value of z is determined from this expression. Ne equals to n equals to v, and this no, lambda q and lambda q, and this. Now, if the actual number of particles exceeds this limiting value, okay, limiting value means this limiting value, actual particle exceeds this limiting value, then it is natural that excited states will receive as many particles as they can hold, namely this, and the rest of the particles will be pushed back to the ground state. This is it. And therefore, n0 equals to n minus this ne. Okay, it's the number. Now, z is then determined by the formula z equals to n naught by n naught plus 1. So 1 minus 1 by n naught. I mean, you can write this way, this inverse, and then expand it 1 minus 1 by n naught. Now, as n naught tends to large, and therefore z tends to 1, right? So when z tends to 1, then your number is pretty large, right? N0 is pretty large, or vice versa. Okay. So this curious phenomena of macroscopically large number of particles accumulating in a single state, the ground state, is generally referred to as the phenomena of, as I said, Bose-Einstein condensation. And this is very similar to the case of vapor condensing into liquid, but there is a difference. What is the difference? In this case, it is the accumulation of the states in a particular state in a particular it's an energy state. Okay, so this is not a real space. It's the energy space. This Bose-Einstein condensation is purely quantum phenomena, and the condensation takes place in the momentum space, not in the coordinate space. Okay. So you see, so the condition for appearance of Bose-Einstein condensation is n greater than this. Okay, n has to be greater than this, and therefore the condensation then starts at when T. Now, if you keep everything constant, say if you keep V and N constant, now if you vary T, naturally, you are going to affect the inequality or equality. Then, if these and these are constant, then your T is less than you take everything on this side, and then take whole to the 2/3, right? Then T should be less than Tc, which is defined like this. So this T is less than, this is a less, and then take all the other side, then that value would be the Tc, and that is what it is. So when T is less than Tc, then we have the Bose-Einstein condensation. Now, symbol Tc is the characteristic temperature, and it depends on mass, because all the expressions in the expression you have this mass and the particle density in the system. Accordingly, for T less than Tc, the system may be looked upon as a mixture of two phases: gaseous phase consisting of the particles in the excited state, and the particles distributed in the particles in the excited state, and condensed state, that we say particles in the accumulated in the ground state. Okay? Now, for condensation to occur, n is greater than this. From this, if n and is fixed and T varies, then of course certainly you can have n as in terms of Tc, and Ne. Ne is like this at some temperature, and then you take the ratio, then Ne by Ne means number of particles in the excited state, is the total number of particles, and this is like this. If you plot this, then you will see this is the fraction n0 by n, and this is T by Tc. This is less than 1, means it is T less than Tc. At this point, much less than Tc, it is totally all are in the condensed state, and then certainly this is decreasing, number of particles in the excited state increasing, and at this point all the particles are gone to the excited state. So this is the kind of Tc. Okay, so now let me go over to this. Now look at the PT diagram for this system. Okay, PT means basically, if you look at this expression, P by KT is this, P is KT by lambda Q, G 5 by 2Z, and for T less than Tc, you know that you have Z equals to 1, and hence for P less than Tc is KT by lambda cube, because P by KT was like this, 1 by lambda cube, this 5 by 2, right? Now, since T by Tc, Z is 1, and therefore it is xi 5 by 2, because it was G 5 by 2 function of Z, and now Z is 1, and therefore xi 5 by 2, and therefore P at Tc equals to, this is the expression, and so your Tc, we have already obtained Tc like this, and then you can write KTc to the power 5 by 2 is of this form, and eventually if you just do this algebra a little bit, then PTc would appear to be n KTc by V. This is xi 5 by 2, it is xi 3 by 2, and if you take the numerical values, it will be 0.5134 times n KTc by V. You see, when this is 1, then it is kind of classical pressure, right? But you see, the pressure has been reduced to half. So the pressure of ideal gas at transition temperature is about half that of the classical gas. It reduces because particles condense to the ground state. Now, if you look at this one pictorially, that this is reduced pressure, and eventually it will merge at large temperature when all the particles within the excited state. then you will see it will merge to the classical value. Okay, and you can just go through you know, this series expansions and see that with these values you can get it. Slope of the now again, if you come back to specific heat, as I said, it will have a cusp. Okay. Um, with no this expressions, these two you have master equations actually, one in terms of p by kt, another time these are the two equations, and you play with that in different limits. Okay, so this is del delta t by 2 pv, and just you kt p, kt p by kt is this, and the put these expressions when t is less than t, c, z is approximately 1. Eventually we'll see that it goes over as if it is t to the power 3 by 2, and that we will have the value like this. If you recall tc, and eventually we can put it here, this kind of value cv by nk, which is 1.9. Actually, classically 3 by 2, right? Means 1.5. Okay. Now you see at t equals to tc, if you put these values, and this is not very difficult actually, just using the relations. So it will have the value 1.9, which is and this is significantly higher than the classical value. For t greater than tc, then again you can have the values, and eventually you will have this kind of expression. Okay. Let's go through this. Nk is this minus this, and eventually if you plot it, then you will see this is t by tc. So value it goes like this, and when t is pretty large, of course it is t by 2 nk, and then as this cusp, and then eventually at t equals to 0 it goes to 0. So this is what it happens, and there is a cusp here. So certificate will be discontinuous here, and that's why it is said that the system is transition. Okay. Now it may be noted that a similar kind of behavior or specific. Now this is both gas or non-interacting gas, basically non-interacting gas. Even though it is not purely perfect theory, I would say, because you think particles having obeying the Bose statistics, and eventually you find that C this form, and therefore you suspect that it goes through a phase transition, kind of phase transition. Of course, in second order phase transition, because second derivative of u is discontinuous. Then observations, and then try to relate it with this Bose theory. And that is what I'm saying here. It may be noted that similar of liquid helium-4 was observed, and that promoted that London to suggest 19 years phase transition that occurs in liquid 4 at a temperature about 2.19 degrees, manifestation of the Bose-Einstein condensation taking in the liquid. Okay, so kind of condensation. So all these are not contributing to pressure and all that. Okay, and that is going to affect many things, even specific heat also, and then it is suspected that kind of phase transition is taking place. And similar kind of behavior has been observed in case of, which is called lambda transition actually, in case of liquid helium 4. And then it was suspected that same kind of phenomena is going to work in case of liquid helium 4. If we substitute the data for helium 4, then Tc turns out to be of the order of 3.13 degree Kelvin, which is not substantially very different from this. Okay, so it is, we can say that kind of close enough. Okay, and which is not drastically different from the observed transition temperatures of the liquid. Okay, moreover, this interpretation of phase transition in liquid helium 4 as a weak condensation provides a theoretical basis for the two-fluid model of the liquid. And according to London, N0 particles that occupy a single energy neutropilus state, epsilon N0, could be identified as superfluid. Okay, so they are flowing without any, you know, friction or viscosity, etc. And the rest n minus n0 particles that occupy the excited states correspond to the normal fluid. At t equals to 0, all the particles occupy epsilon 0 state, and hence the liquid goes over to the superfluid state. Since there is a difference between the experimental value of Tc from the simple Boltzmann and Tc, Vernon thought that in interparticular interaction, maybe, as I said earlier, I just mentioned that it is not that I won't is a very perfect one, because it was assumed that these particles are non-interacting. Now, if they interact with each other, then some contribution should be taken into account, right? And they will have some contribution to the theory, and therefore that is what here it is mentioned here, that interparticle interaction may be responsible for such discrepancy in TC. In fact, the inclusion of interaction improved the TC. However, there has been other advances in the fluid. So basically, in this, we give a message that we understood that what is happening, that at some temperature, if the temperature is, varied, then you will see that from classical regime it goes over to, it departs from the classical regime, and eventually it shows some kind of accumulation of momentum in space. Not real momentum, the kind of particles are getting accumulated in the ground state, and that is increasing as temperature is decreasing. And these are manifested how it is manifested in terms of macroscopic quantities. Pressure, becomes reduced, then the specific heat is fast, and it sometimes it goes beyond the classical value, and it shows kind of phase transition. And then you have the observation of if you want to explain how this kind of stuff is happening in liquid helium 4. It is a transition from normal fluid to superfluid. How do you explain it? Probably you can explain it in terms of this Bose-Einstein condensation postulate, and that also turns out to be close, not exact, but close enough. And pointed out that there could be, we did not take into account the interaction between particles. If we take into account, that might improve the TC. Now, I'm not talking about it, but I'm going to relate with something which is known to you. Okay, for example, the application of B statistics. There are many applications actually. At least there are two important applications are there. One, you have already done it from the BSc course. What is that? That radiation, I mean, black body radiation that you have studied, right?
Yes, sir.
So in the black body radiation, you have photons, right? You have a cavity, and there are photons, and then that photon gives you some kind of spectra. That cavity gives you some kind of spectra, and you try to analyze. You have the experimental observation, the radiation spectra, and then you want to analyze it. And then what did you do? Actually, this problem has been looked upon from two practically identical but concepts. Number one, as an assembly of harmonic oscillators but with quantized energies like this. And number two, two identical indistinguishable quanta, that is phonon, the energy of a phonon corresponding to angular frequency omega s. Now, now photons, light actually. Photons are bosons, you know that, because it has an integral spin, and also they have quantum characteristics, and therefore you will have the coefficient number like this. However, in this case, one more important thing is that the number of particles, number of photons are not conserved. And therefore, if the photons number is not conserved, then alpha is zero in the when we talked about the Lagrange multiplier, then this will be zero, and this will be zero, right? Because otherwise it will need energy or it will gain energy, right? If it is zero, then number of photons can be anything. Whatever it does, so number of photons will not be conserved, and therefore that the consequence is mu has to be zero, chemical protein, and therefore number average occupation number will take this form. And once you know this, then you know the density of states, right? Number of states having the you know what to do, right? If from the phase space, you see the number of states multiplied by 2 because of kinds of polarization, and then get the density of states and number of average number of particles, and then each one having h cut omega. They multiply the energy, so density of states and average, and then number of particles in the states multiply, and then each one have energy this, and then integrate over. So that's how you get the density of state. And this expression does the black body as the spectral behavior of black body radiation, right? And another application is, I think, I don't know whether have you. I think you all of you have read the specific heat of solids. So did you go through them earlier? Specific heat of solids,
হ্যাঁ
device theory, Einstein theory.
করেছি, কিন্তু মানে স্ট্যাটিস্টিক্যাল অ্যাপ্রোচে করেছি কিনা তা তো মনে নেই।
No, of course you have done, because you have taken same thing you have done, na? There also you have I mean, average occupation number you have considered there, right?
হ্যাঁ,
Energy you have calculated using that. So basically, you have used that average occupation number for those things, and therefore that is yet another application. Okay, so just go through and I think mm, so Thursday.
চেক করে দিয়েছি আমি তো।
হ্যাঁ স্যার।
Okay, maybe this is the last class, because the 20 second moderation, there will be moderation 22nd, and even if I start something like Harvey gas, then probably I will not be able to complete it. So let me know if you have any questions, anything, then you can ask me. But before that, I would say that firstly, look at the previous year questions, because you can look at the questions, but do not avoid such questions, because my belief is there is no hard and fast rule that I have to avoid the last year question papers, because this is the material to ask question from anywhere. It can repeat, it may not repeat. Okay, so this is kind of word of caution I'm giving you, that many to avoid the last year question paper. They try to skip the portions which have already appeared. For this course, please do not skip, because I believe that if I cover something, then I'm supposed to cover it. Now, secondly, I would ask only 6 questions. Out of that, maybe one question may be common. Okay, so 6 questions. Then first question you have to answer. All have to answer first question, and then 3 from the rest. Okay, same I'm going to follow. Okay, and I think you have got enough materials to study. So, I mean, Dibyendu,
Yes, sir.
did you study all the materials that I have supplied, or have you read everything from the Patria?
না স্যার পুরোটা হয়নি, চলছে স্যার, পাত্রিয়া থেকেও পড়ছি।
Because I'm religiously following Patria, right? So,
লাস্টের দিকে।
right?
হ্যাঁ স্যার।
So then it is very convenient for you, right? You don't have to books and notations, and so try to spend your most of your time. What else can I say?
স্যার পরের ফার্মি সিস্টেমের জন্য আপনি কি নোট করেছেন?
নোট কি করবো ভাই, নোটটা আমি এটা করি যাতে কিছু এক্সট্রা স্টেপ গুলো করার জন্য। দ্যাট ইজ দ্য
ওইটাই।
হ্যাঁ, একটু দেখে নাও, একটু করে নাও পাচ্ছিয়াতে। তোমরা কি চাও আর একটা ক্লাস নিয়ে আমি? তাহলে আমি বৃহস্পতিবার মৌসুমী
স্যার মানে ক্লাস নেবেন সেটা ঠিক আছে, কিন্তু ওটা সিলেবাসে আবার থাকবে স্যার, ওই যেটা যে আজ পর্যন্ত পড়ালেন সেটা থাকলে ভালো হয়।
আচ্ছা 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 আচ্ছা। কিন্তু তোমরা কি বলছো?
স্যার আজ লাস্ট হলেই ভালো হয়।
সিলেবাস বাড়তে চাইছেন স্যার আমরা একটু।
আচ্ছা দিব্যেন্দু,
হ্যাঁ স্যার।
হ্যাঁ, তোমার যদি কোনো জায়গায় বুঝতে অসুবিধা হয়, ইউ ক্যান অলওয়েজ কন্ট্যাক্ট মি। ওকে
ওকে স্যার।
I will stop here for this course, and you prepare yourself for বেরিয়ে যাই তাহলে।
স্যার বলছি কি ডেনসিটি ম্যাট্রিক্সটাও কি আমাদের এসে থাকবে, মানে কোশ্চেন?
আমি পড়ালাম তো।
না, এর আগে মানে সেকেন্ড সেমে শুনেছিলাম আপনি বলেছিলেন কি যেটা আপনি মানে অ্যাসাইনমেন্টে দেন সেটা সিলেবাসে থাকে না নাকি, ওই জন্য
অ্যাকচুয়ালি অ্যাসাইনমেন্ট কি দেবো আমি সেটা ঠিক করতে পারছিলাম না। তখন সুমন বললো দিন সামথিং কিছু, মানে আপনি কিছু দিন যেটা আমরা শিখতে পারবো। যদি ওটাকে না পড়াই তাহলে আমি বোস গ্যাসে ঢুকতে পারবো না।
ওকে স্যার।
তো হ্যাঁ হ্যাঁ হ্যাঁ, আর সুমন কিছু ওকে, ঠিক আছে, আমি তাহলে বেরিয়ে গেলাম। হ্যাঁ, হ্যালো, বলো গোবিন্দ।
হ্যাঁ স্যার, বলছি যে আমাদের যে দুটো ইন্টারনালের ওইগুলো মার্কস গুলো কি আমরা ফাইনালি জানতে পারবো একবারে?
এত গুলো পাতা তো, এবার সমস্ত কম্পিউটারে বসে বসে দেখতে হচ্ছে, মানে হার্ড কপি হলে মোটামুটি একটু তাড়াতাড়ি কম্পিউটারে দেখতে হচ্ছে, ওইখানে ওই মার্কস দিতে হচ্ছে, এ করতে হচ্ছে, একটু দেরি হচ্ছে। আমি হয়তো আর 2 দিনের মধ্যে আমি তোমাদেরকে পাঠিয়ে দেবো হোয়াটসঅ্যাপ গ্রুপে। হ্যাঁ, আই উইল আস্ক ইউ টু। ঠিক আছে,
হ্যাঁ স্যার।
ওকে, বেরিয়ে গেলাম তাহলে।